Okay, in this video, we're going to be looking at how we can graph out position versus time to show how fast something is moving, either as its speed, where we don't care about direction, or as its velocity, where we do care about direction. Speed and velocity are talking about the same thing, how fast something's going, but speed is a scalar quantity, which is a fancy way of saying the scale of the number is all that matters, so how big or small it is. For velocity, it's a vector. A vector just includes a direction. So we are also talking about whether it's going up, down, left, right, backwards, forwards, this way, that way, north, south, east, west, something like that. So graphs can be extremely helpful for processing a lot of information about where something is going and how fast it goes there and how long it takes to get there. So let's look at some examples of how we can do that. So our first example has to do with a hummingbird. It's going up and down and up and down, drinking nectar from flowers at different heights, maybe on a bush or something like that. So the graph down here shows how the position of our hummingbird changes over time. So on the y-axis, we have how high up or down the bird is off the ground. So this kind of zero mark down here is going to be the ground. Okay, so this would be the ground at 0. All right. And then along the x-axis down here, the horizontal axis, that's going to be time. So time is going to continue moving on this way. So at first glance, this graph kind of looks like our bird is moving down and to the right, and then up and to the right, and then down and to the right, up and to the right, and then down and to the right. But really what's happening here is that the bird is just moving downwards, but time is moving on as it does so. And the bird moves upward as time goes on. And the bird moves downwards again as time goes on. And then the bird goes up as time goes on. And then the bird goes down as time goes on. So if I can just draw little arrows here in red to show how the bird is moving. There. Go to about there. Down to there. And that one there. Okay, so what's in red is showing how the bird moves. And left to right, it's in the same place. It's just moving down, and then a little up, and then a little more down, and then a little more up, and then really far down. Okay, whereas these blue arrows I'm going to draw in are just showing how time continues to go on. So it moves up and down as we have like a timer running or something like that. Here, there, and there. Okay, so let's look at this first set of questions that goes along with this. Based on the graph, the hummingbird flew. Okay, so it's either going up or down during these segments. All right, and we can tell that as time is going on, the distance from the ground is changing. So our bird started up high and then wound up lower as time went on during segment 1. So the bird must have been going down for segment 1. In segment 2, the bird winds up higher than it was before. As time goes on, it ends up getting to a higher distance up off the ground. So the bird must have been going up. And you'll see that kind of alternate. In segment 3, it goes down, and the bird goes back up again, and then finally the bird goes down a lot in segment 5. Okay, so that's what we're showing on this graph. Okay, the red arrows are just showing which way the bird is flying, either downwards or upwards, and the blue arrows are just showing that time continues to move on and tick up and up and up as the bird goes up, or it goes down and then up and then down and then up and then down a whole bunch. Okay. This graph can also tell us other information besides whether the bird is moving up and down and stuff like that. It can also tell us how fast the bird is moving. So let's look at some examples like that. So let's go on to the next question. Hummingbird flies up and down. Okay, so that's the same stuff, same graph. But now we're going to be looking at the speed during specific segments of this graph. So we want to calculate the speed during segment 1 and during segment 5, where the speed is just the distance divided by the time. Okay, so let's go up here to look at segment 1. All right, so the distance that the bird travels is already kind of outlined here. It says off to the side that the distance is 3 meters for segment 1. So this little 1 down here by the D means the distance of segment 1 is 3 meters. Okay. If you want to see that for yourself on the graph, this is where our bird started, okay, up at the 6 mark. All right, and it winds up down between the 4 and the 2. So this is like right in between 4 and 2. So this must be at 3 meters. So if our bird went from 6 down to 3, it traveled down 1, 2, 3 meters. Okay, so the bird has moved 3 meters in segment 1. Okay, and as it moves, time goes on. So let's check the time. So we started the timer at 0. Okay, so this is segment 1. And then the segment 1 ends at a time of this. So let's see where this winds up. Okay, so we started at 0 seconds. And this goes on until we're right in between 2 and 4. So this must be 3 seconds. Okay, so to get from beginning to end here, it took 3 seconds. All right, so the speed of the bird during segment 1, I'm going to call S1 for the speed for segment 1. That's going to be equal to the distance that the bird moves, D, divided by the time it takes for the bird to travel that distance. Okay, so D divided by T, and more specifically, the distance in segment 1 divided by the time in segment 1. That's going to be our 3 meters of distance as the bird goes 3 meters downwards, divided by our 3 seconds of time that it took for the bird to get there. So if you plug this into a calculator, or if you have some very good mental math, you might know that 3 meters divided by 3 seconds is just going to be 1 meter per second. 1 meter over 1 second. So our answer is going to be 1 meter per second. Okay, that's the speed during segment 1. So I'm going to write that down here. 1 meter per second. Okay, now we can do the same thing for segment 5. So let's do that next. All right, so this one's like all the way over here, so it might be a little bit harder to read on this graph. So we're starting segment 5 here. We're ending segment 5 here. Okay, so if I kind of take this back over to the axis to see where this is at. Okay, so this is in between 4 and 6. So we're starting at a distance of about 5 meters off the ground. Okay, and the bird goes all the way down to the ground, down to here, okay, which is at 0 meters. Okay, so from 5 down to 0, the bird went 5 meters down. Okay, which is why we have this D5 equals 5 meters. Okay, our time of segment 5 starts here, right there, and you can kind of track that down, and then ends here. Okay, so let's see. If our time on this x-axis here is in between 8 and 10, this must be 9 seconds. And then this is right on 14. So how much time is in between 9 and 14? That is 5 seconds, which is where we get this 5 seconds here from. Okay, so let's calculate the speed of this segment too. So segment 5 is going to have a speed of, so I'm doing S5 for segment 5, equals, all right, my distance, which is 5 meters downwards, 5 meters divided by the 5 seconds it takes to get there. Okay, and again, you can either plug this into a calculator or use some good mental math. And hey, this also winds up being 1, I'm running out of room here, meter per second. Okay, just like segment 1. Okay, now you might actually be able to see this if you compare the slopes of segment 1 and segment 5. So let's go back up here for a second. So if you kind of compare the angle of how segment 1 is going down like this, and you look at segment 5, it's going down like that, the slope or the angle is about the same for those two segments. Okay, you can even break this up into smaller chunks and see that the speed is 1 meter per second. So if you're starting back at segment 1, if you go down 1 meter, that takes 1 second. And if you go down another meter, that takes 1 more second. You go down another meter, okay, that takes 1 more second. It keeps going like that. Even something like segment 3 has this going on too. You go down 1 meter, takes 1 second. Okay, it even has the same thing in the other direction for segment 2 and segment 4. So if I go up 1 meter on segment 4, that takes 1 second on segment 4. Okay, that's true the whole way through. Everywhere on this graph, our hummingbird has the same speed. It is moving at 1 meter per second. The only thing that's different is which direction it's going in and how long it continues at that speed. Even though segment 1 is shorter than segment 5, and even though segment 4 is going in a different direction than segment 5, these are all just the bird moving at 1 meter per second in a different direction or for a longer duration of time. Okay? So the slope can be a handy way to figure out how fast or slow the bird is moving on a graph like this, where you have position, like how far up or down or left or right, is compared to time on the x-axis. Okay? You might even know that the slope of a line, slope, is equal to the rise divided by the run. Rise divided by the run, okay, or the y divided by the x. In this case, our rise, or our y value going up and down, is our distance. Okay, and our run going left and right, our x, is time. Actually, let me write this a little bit better. Okay, our rise is distance, our run is time. That's our y over our x. Okay, and distance divided by time is the speed. So on a graph like this, the slope of the line is the speed of that object, in this case, a hummingbird. Okay, so we can compare how fast or slow something is moving just by comparing the slopes of these lines. Okay, let's see what other questions are on this page. Okay, the bird's speed during segment 1 is the same as its speed during segment 5. Okay, and the slope of segment 1 is the same as the slope of segment 5. In this case, since speed and slope are basically showing the same thing on this graph, the same slope means the same speed, and the same speed means the same slope. Okay, let's look at another problem. This one has to do with a drone. So a student flies a drone up into the air, has it hover for a second, and then they bring it back down to the ground. Okay, to show that, we have another graph that has up and down on the y-axis, and our left and right is time. So as time goes on, our drone goes upwards a whole bunch, and then upwards a little bit more, and then upwards a little bit more, and then upwards a tiny bit more, and then it stops for a bit until it goes downwards a little bit, and then downwards a little bit more, and downwards a little bit more, and downwards a lot. Okay, all while time goes on. Time goes on, 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 even when it's not moving, time goes on. Time, oh, here, actually, let me put it underneath like so. Time goes on, time goes on, time goes on, time goes on. Okay. Now, just by looking at this, you might notice that the slopes of these lines are different. Okay, where you have like this very steep slope for segment 1, but then segment 2 is a little bit more shallow. It's a little bit flatter. Segment 3 is even shallower or flatter than that, and so is segment 4, until segment 5 is just totally flat. It's just totally level, like horizontal. And then segment 6 starts going the other way. It starts sloping more, but now it's turning downwards instead of upwards. Then it goes a little bit more downwards, a little bit downwards, a little bit downwards. And you keep getting a steeper and steeper slope again. Whether your line is going up or down as you go left to right, the steepness of the slope tells you how fast something is moving. The steeper the slope upwards or the steeper the slope downwards, the faster the object is moving, because you're covering more distance in some amount of time. Okay, if your line is kind of flatter, if it's not as steep, if it's shallower, then you're not covering as much distance in some amount of time. If you kind of compare these blue arrows, all these segments of time are about the same, but you're either covering a big distance or you're covering a small distance. So let's see what their questions are asking for. First off, we want to compare the slopes of these lines and the speeds or the velocity, so speed in a specific direction, between segment 1 and segment 3. So let's compare these. So in segment 1, we've got a really, really steep line, so a steep slope. In segment 3, we have not so steep. So segment 1 is steeper than segment 3, which should mean that segment 1 is showing the drone moving faster than segment 3. Okay, where again, velocity is just speed with the direction. In this case, the drone starts by moving upwards, and then it kind of stops for a second, and then it moves downwards. Okay, so this is saying that the drone starts by moving up very quickly, and then it slows down, slows down, slows down until it stops for a little bit of time, about 2 seconds, and then it starts to move downwards a little bit faster, a little bit faster, a little bit faster, a little bit faster, until it eventually reaches back to the ground. Okay, if we want to know exactly how fast it's moving, we can calculate that using the graph. Okay, so this looks a little bit different, where we have a v there for velocity, and we have a y there instead of a d. So talking about vertical distance specifically. But other than that, it's basically just that the speed is equal to the distance divided by the time. Okay, we're just writing it a different way. Okay, in velocity, we typically use displacement, which is a fancy way of saying distance from one position to another. Okay, so if we look at the displacement in segment 1, we're starting here and ending here. Okay, we go from 0 meters to 4 meters. Okay, if you want the official way to calculate a displacement like this, or any change, okay, this delta, this triangle thing, ooh, that was a weird pen mark. Okay, this delta, let me write it down here, just means a change in something, whatever it's before, which means you take the final value. Ooh, pen keeps doing weird stuff. The final value minus the initial value. Okay, so the displacement here officially would be delta, which is the change in y, which is our vertical measurement here, okay, how far up or down it goes, for segment 1 equals our final position, upwards or downwards, which is 4 meters, minus our initial one. Our initial position is at 0 meters. So our change in position here is just going to be 4 meters. Okay, now you could also just count it out and say in between 0 and 4 we have 4 meters there. But this will also help you figure out the direction of where it's going up or down. Since up is going more positive on the graph, then if we get a positive answer, that means it's moving upwards. Since going downwards is going more towards the negative, if you do the subtraction of your final minus initial and get a negative number, then your object is moving downwards. Okay, time should always come out to be a positive change because your time is always moving from left to right. Okay, which is kind of nice. So let's do that. Let's calculate the time for this. Our delta ti, so the change in time for segment 1 is equal to, well, we ended the timer at here, which is 2 seconds, minus where we started at, which was 0 seconds. So we ended at 2, we started at 0. So 2 seconds minus 0 seconds is going to be 2 seconds. Okay. Now, we can use this to calculate the speed at segment 1. Okay? Or more specifically, the velocity. Okay? The velocity of this is going to be equal to our speed, or sorry, our displacement, our change in y, which was 4 meters, divided by the time, which was 2 seconds. So 4 meters divided by 2 seconds is going to be 2 meters per second. That's our velocity here. And actually, technically, I should go back and fix this. This is kind of a specific thing. It's not super important, but really we're just calculating the velocity, not the change in velocity, so I should have left that out. Okay, so this is our velocity for segment 1. It's going at 2 meters per second. Next, we're going to calculate the velocity at segment 3. We're going to do basically the same thing. But we should get a slower velocity. We should get a smaller answer because we have a kind of a flatter slope and we're not covering as much distance in that amount of time. So let's do V2 equals, and I'm going to kind of do the shortcut version this time. We're going upwards by 2 spots. Okay, so our change in y is going 2 meters, or sorry, oops, I got to be careful about this. Watch your axis. Okay, we're starting at 6, and we're going up to this part here. If you kind of look at how your axis is set up here, from like 2 to 4, that takes like 4 of these blocks. So like this guy would be 3, this guy would be 5, this guy would be 1. After this, this should be 6, 6.5, 7. So we're only going up by 1 meter. Okay, so our distance, or our change in vertical position, or our displacement, all mean the same thing. It's just going to be 1 meter. Okay, our time is going from here to here. Okay, in other words, from 4 seconds to 6 seconds. Okay, so you could do a final minus initial and do 6 minus 4, or you could just say from 4 to 6 seconds, that's 2 seconds. So if I take 1 meter divided by 2 seconds, you can write it either as this kind of flat fraction, or you can do it kind of as a diagonal. 1 divided by 2 is 1/2, or you could also write it as a decimal form as 0.5, which I kind of like better. And whoops. There you go. And now our units are meters per second. All right, so let's write that down here. 0.5 meters per second. Cool. All right. So we can calculate velocity basically just like we calculate speed. It just takes a little bit more attention to detail to make sure that we have our direction included. And that can kind of reveal itself as you do your final minus initial measurements. Okay, this graph is going to look kind of weird because instead of looking at this in terms of up and down, we're now going left and right. Okay, time is still going to be moving onwards as we go from left to right. Okay, but now up on the graph where you're getting more and more positive means the object is going to the right. And down means you're going to the left, okay, where you're getting more negative. Okay, so this is kind of like you're tilting your head and looking at this graph wrong, okay? Or maybe you could turn your screen like this, and then you might be able to kind of see it a little bit better, where your left is going this way and your right is going this way. Most of the time, in graphs like this, we will just kind of by convention, by tradition, put time on your x-axis. So even if your object isn't moving upwards or downwards, we'll put the left or right or backwards or forward position on the y-axis, going up and down. So this graph is going to look a little funky, okay? And it's going to take a little bit of thinking through to figure out exactly how this object is moving. So here we have a pendulum that's moving back and forth, back and forth. It starts very far to the right and then goes to the left a whole bunch, and then back to the right, back to the left, 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 and then finally ends in the middle. You'll see that the middle, okay, where it's hanging just straight up and down, is 0. Okay, and this time we're measuring this in centimeters, so this is 0 centimeters. All right, if you go to the right, that's going positive 1 centimeter, 2 centimeters, 3 centimeters, 4, 5. So we're starting at positive 10 centimeters. Okay, and if you go to the left, you're going down at the negative numbers. Okay, from that 0 position, you're getting down to negative. So this is our middle point. If you go off to the left, okay, well, what would this be here? Well, this is 5. This is 10, negative 5 and negative 10. So to get there, we go 1, 2, 3, 4, 5 spots. So to get from negative 5 to negative 10, each one of these must be like 1. So like negative 5, negative 6, negative 7, negative 8, negative 9, and then negative 10. So our pendulum's going from positive 10 to negative 9 all the way down that way. Interesting. Okay. So let's look at some of these questions, and then we can kind of figure out where to go to next. So first off, we want to just rank the pendulum speed from slowest to fastest based on these 5 slopes. Okay, so we're only going to look at segment 1, segment 6, segment 9, segment 4, and segment 10. We're going to put the slowest segments over here on the left and the fastest ones on the right. So let's look at this. Segment 10 is all the way at the end here. Segment 1 is at the very beginning. Okay, and remember that the slope should tell you how fast your object is moving. Since segment 1 has a really, really steep slope, it's almost going like straight down. That means we have a lot of distance that we're covering in a pretty short amount of time. So that would mean it's going pretty fast. It has a high speed or a high velocity. Whereas something in segment 10 is not covering so much distance. It's covering a little tiny bit of distance in that same amount of time. So segment 10 is definitely going to be our slowest moving segment. A pendulum is moving slowest during segment 10. And I'm going to run out of room here. So let me just write the letter for that, which was E. Okay. Whereas segment 1 is going the fastest by far. So I want to put that over here. What I'll do is I'll write the segment number underneath. So this was segment 10. This was segment 1. Okay, let's look at the next slowest. Okay, since our pendulum is moving back and forth and back and forth, and it seems to be slowing down as we go from left to right, we have kind of like very, very fast, and then not quite as fast, but still pretty fast, a little bit slower, a little bit slower, a little bit slower. Our lines are kind of flattening out the further they go from left to right. So the next slowest from segment 10 would be segment 9. And the next slowest from that would be segment 8. And the next slowest would be segment 7 and then 6. But we're not asked about all 10 segments. It's just a couple of them. So segment 9. Let's cross that one out. Segment 9 would be the next slowest. It's close to the end where the pendulum totally stops. It moves so slow it just stops moving. All right. And then segment 6 is going to be the next slowest from that. Okay, it is faster than segment 9. It's steeper than segment 9, but it's still not super fast or anything like that. That would be B. Oops. Or segment 6. And then you have D. This last one. Ooh. Which is segment 4. Okay. So the pendulum starts the fastest and then ends up going the slowest. So it kind of is a little bit backwards. Okay. Now let's actually try to calculate how fast or slow the pendulum is going at some of these segments. So let's go down here. Okay, we're going to calculate velocity. So again, that means we're looking at how fast it's going as displacement divided by time, by change in time. So it's still basically just distance divided by time, but in a fancier way. Okay, and this is also going to include the direction of where it's moving. So there's our graph again. Okay, we want to look at segment 2 and segment 7. Okay, we want to figure out what the velocity is, and then whether it's going left or to the right. And again, we don't really need that delta there. Okay, so let's do segment 2. Yeah, let's do segment 7 first. Let's do segment 7. I think that one's a little bit easier. Okay, in segment 7, we start here and we end here. So let's take this over the axis and see where we're starting at. Okay, we're starting right there. We're ending here. Okay. Now again, to get from 0 to 5, this would take 1, 2, 3, 4, 5 spots. So each one of these blocks is like 1. Each one of these lines is 1 spot. So this would be 1, 2, 3, 4. We're starting segment 7 up at 4 centimeters. And then we're going down to 0. This would be -1, and then -2, and then -3. Okay. So we're going from -4 down to, we're going from +4 down to -3. Okay. So if we wanted to calculate the displacement there, that would be delta y. So our displacement, the change in vertical position, is equal to our final, which is -3, minus our initial, which is 4. We ended at -3. We started at 4. We always do our change in as the final minus initial. Okay, and that's also up here, final minus initial. So this is going to come out to be -7 centimeters. Okay, where that negative means that we're going down on the graph. Okay, and down on the graph for us means this is going left. Okay, so this is saying that our pendulum during segment 7 is going 7 centimeters to the left. Okay, now we want to figure out the velocity. So we know where it's going to be ending up going left, but we still don't know exactly how fast it's going there, how long it takes to get through that 7 centimeters. So let's check that next. Okay. So next we need the change in time, how long it takes to get there. Okay, segment 7 starts here and ends here. So let's track that down. It's right there. Right there. Oh, whoops. Tracked the wrong part on the there's our x-axis there. I guess it didn't need all those marks. So we started here, we ended here. If this is 10 and this is 15, this would be 10, 11. So we start at 12. Just going to write up here. And we end at 12, 13, 14. So our change in time is going to be our final time, which is 14 seconds. Which is 14 seconds, minus our initial time, which was 12 seconds. That's going to be equal to 2 seconds. So let's calculate the velocity. The velocity for segment 7 is going to be equal to that -7 centimeters divided by the 2 seconds it took to get there. And if you plug this into a calculator, -7 divided by 2 should give us negative 3 point. Ugh. The pen keeps acting up. Negative 3.5 centimeters per second. Oh, that was really bad. Negative 3.5 centimeters per second. And it's going to the left. Okay, which leaves just this last part of number 5, figuring out segment 2. Okay, so this is going to cover a huge distance. Okay, and you could do this the official way of calculating the change in y as the final minus the initial. You could also kind of cheat this. So let me show you kind of the cheater's way. So our segment 2 starts here and ends here. Okay, if I just want to know how far this is going, well, each of these blocks is 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I'm going 17 spots upwards. I'm going 17 centimeters upwards. So my delta y is a little bit easier to calculate on the graph because I could just count it out. It's going 17 centimeters. And since we're going up right on this graph from beginning to end, it's going to be positive. My change in time is going to be from here to there, which is from 2 seconds to 4 seconds. So from 2 to 4 seconds, that's 2 seconds of time that goes by. So if I want to calculate the velocity at segment 2, that's going to be equal to the distance that we covered, which was 17 centimeters to the right, aka positive, aka it's going up on the graph. So 17 centimeters divided by our 2 seconds. This comes out to be about 8.5 centimeters per second. Okay, I can go down here, write that in, 8.5. Okay, and this time this is going up on the graph, which means it's going to the right. All right. So whether you're doing velocity or speed, the calculations work basically the same way. And on a graph, you can tell relatively how fast or something is moving or how slow something is moving without even having to calculate, just by comparing the slope. Because that slope on a graph of position versus time is going to be a rise over run, or a position over time, a distance over time, which is the speed, or which is the velocity. And if you're doing velocity, all you have to do is keep track of the direction something is moving in addition to how fast it's moving.